Okay, so I just defined what a dense set is. Now I'm going to dig deeper and let's look at some examples. Examples of dense sets. Right, it's an example of a dense set. So let's look at a canonical example. Okay, so example number 1. A set of rational numbers. So one big tip is don't confuse the Q, which in latex would be the math BB Q. That one is the set of rational numbers. R does not stand for the set of rational numbers. That one is a set of real numbers. Real numbers contains the rational numbers, but also contains irrational numbers. So keep that in mind. And the symbols could be misunderstood, so I just want to get that clear. This is specifically for rational. So rat. Okay. Let's do a proof. Hope you all are ready for this. I'm not prove it. So let's say. So we're just going to say it's dense in R. Before I do that proof, I just want to talk about the intuition as to what I'm trying to show. Okay, so remember I had a little s contained in big S, and that was contained in x, and then x is contained in the real numbers, correct? So we know q is contained in big R, right? This is something we know, because I just explained how the set of rational numbers is not the real numbers, because the real numbers can contain irrational numbers, right? So this is not, they're not one-to-one, they're not bijection. Sorry, they may be one-to-one, but they're not bijection, right? So with this being said, what can we see here? In this path that I drew, this Q is very much like this X, but it could also be S. So we have to think which one. I think, and hopefully maybe you can pause the video and try to guess, the Q is S in this context. The reason why we want Q to be S in this context is because we're going to have to prove this, and if we're talking about S, we'll most definitely be talking about the elements of S, which is going to be described in lowercase s. So this is a very direct relationship. If we were to call Q X, then there would be not as concise, because we could, for all we know, we could be talking about lowercase x. So our proof would look like essentially something like this. And then our elements for Q are according to S in this relationship. Okay, so hopefully this makes sense. So we're just disregarding the X because we're making direct proof from this S to R. Okay. So we're going to talk about taking Q in R. Right? We know Q is in R because Q is in big Q. Now let's just write Q n plus R. This is all arbitrary, right? And then you do need to know n is contained in the set of integers, and 0 is less than or equal to R, less than or equal to 1, right? So we're going to make the decimal expansion right now. So what I just showed you was Q is just some arbitrary real number. Kind of like epsilon, it's arbitrary. For all we know, it could be 1, 5, right? So calling it the sum of two variables is fine. So we have n containing z, and 0 is less than or equal to r and less than or equal to 1. Now we have this decimal expansion. Point R1, R2, R3. So each of the indexes represents the place past the decimal. And then we're going to make another arbitrary phrase, xk. This guy's going to be n plus r1, r2, rk. This is a decimal point. So what this tells us is we're going to have this q become basically xk, but it stops at a certain digit when we get past the decimal. That's something to keep in mind. So then what that means is xk minus x, the actual value, is going to be less than or equal to some epsilon. Right. So then now we write limit, because like I said before, when you see this notation, think convergence, limit, MCT. I said that in the previous upload, so if you need a refresh, please check that one out. And then k going to infinity. Xk. And this was the criteria to show that whichever, because x was in R, right? And I believe xn is also contained in R. It's showing that, hey, R has something that's, and most importantly, it's contained in Q. So, why would I say it's contained in Q? Well, we can go back. K is a defined number. K is a natural number, not just an integer. It would make sense for K to be an integer because then the indexes would be negative, right? And we only want stuff after the decimal point, and the first natural number is 1. So xk is going to be a discrete defined number because the decimals are defined, but r may not be. It may go all the way to rn, and we don't know what n is. That's why we're trying to estimate it with xk. And we know xk is in this set, q and in r, right? So here I prove that Thus Q is, which is a set of rational numbers, is dense in R. So one way to think of this is, we know there's two sets involved. R, the real number, the biggest one in this context, and the smaller one that's specified, which is a Q. And we want Q to have some sequence inside it based on its properties to converge to this arbitrary value we seek, which is x in this case. So that's the way to go about these, and I hope that helped proving things are dense with this canonical example.